This is where I messed up. Assume you have one gram. Yeah, that was wrong. Assume you have 1 gram. That means you have that much carbon, 0.067 grams of hydrogen, 0.5 grams of oxygen. Okay, that's what you do. This is percent by weight, not percent by moles. It's always percent by weight, not percent by moles. All right, so it is a longer walk. If I have 0.400 grams of carbon, grams, moles, carbon. 1 mole of carbon is 12.01 grams. If I have 0.067, I guess that's all we have for significant figures there. Grams of hydrogen. 1 mole of hydrogen is 1.01 grams. Hydrogen 0.533 grams of oxygen. Grams of oxygen. Moles of oxygen. 1 mole of oxygen is 16. Okay, now I'll do it that way. 0.4 divided by 12.01. .067 divided by 1.01, 0.0663 moles of hydrogen. That's really 2 significant figures, but I should have had a 0 there just to make this easier. 0.533 divided by 16.00. This will come out to a real molecule this time. All right, let me work over here. 0.0 oxygen was 0.3. Okay, divide all of these by the 0.066. Smallest number, we get 0.333 divided by 0.0663. H, that's going to be 1. Oxygen, that's going to come out to the same. Is that what it came out before?
I think you forgot a 0.
Where did I forget the 0?
Okay. 0.033. Unless you divided both.
This one?
No, I think you wanted it there.
Oh, this 0.
Yes, sir.
It should not come out. More of those to more of those. Is this going to come out sensible this time? All right, so now we're dividing like that. See, so that's going to be 1. That comes out to about 2. That comes out to 1. Okay, good. That's a real molecule. Thank you. I like to practice these things before class. like I said, I came in this morning and realized we don't have lab. Finish empirical formula. Okay. Here's the molecule that would be. Since we haven't talked about this yet, you wouldn't know this. Carbon makes 4 bonds. It's making 2 bonds there, 1 there, and 1 there. Oxygen makes 2 bonds. Hydrogen makes 1 bond. So that's a legit molecule. But if we multiply through by 2, there is a molecule, H4. Two oxygens. Yeah, if I really wanted to do it, I guess I'd have to do this. 1, 2. I shouldn't waste time trying to do this, but that's a legit molecule. Carbon makes 4 bonds, carbon makes 4 bonds, carbon makes 4, oxygen makes 2, oxygen makes 2, and each hydrogen makes 1. So these 2 are part of a family that goes 2, 3. So there's another structure that goes with that. Anyway, that's empirical formula. I don't want to hang on it because it doesn't mean much going forward. Let's go on to something that really matters, at least in terms of the world of chemistry. Because very few people do combustion analysis anymore, given that there's much better techniques to find out what you've got. Let's go on. Something I'm sure I can do. This takes us to the next section. And we generally always mean concentration in a liquid. So just as an intuitive way to look at it, you make these about the same size. Liquids say water, and I've got something dissolved in it. So you can take something like NaCl, dissolved in water. For the same amount of water, I've got, actually I counted the dots, I've got three times as many dots here as I have here. This one is more concentrated. You understand that, just visually what that means. Concentration always means some amount over another amount. And it's always the thing that is dissolved into the other thing is called the solute. The thing that you have in bulk is called the solvent. So what you have more of is the solvent. What you sprinkled in there is the solute, just for some vocabulary. The concentration is always over the amount of solvent. You can do amount in grams, you can do it in moles, but in our case, there's a specific case where we're going to do the amount of moles and I should say solution. Chunk of NaCl that I'm about to put in. If I'm like this, I have what's about to become the solute and a pure thing of the solvent. Once you put them together, this is called the solution. Just, again, vocabulary. It doesn't work out that you can just put solvent down here. I have to say solution, because when you dissolve things in water, it might change. Like, this might have been, the level of water might have been up there, and if I measured that volume, I'd say, okay, that's how much I have. Once you put your solvent in, or your solute in, it very frequently changes the volume a little bit. So this is the amount of solute in moles. And this is the amount of the resulting solution. You can actually measure how much is there. In liters. And that's a specific definition. We generally just say moles per liter, but it's also represented as a capital M. The capital M is superfluous. You can always just say moles per liter, which I tend to stick to. But know what the M is, because everybody uses the M. So based on that little bit of information, you can have, this is example 3.14. So this is the solution. Obviously, soft drink isn't a pure anything. It's got lots of stuff mixed in there, including sugar, which is where this is going. It tells you that all of these, moles per liter, capital M, molarity, and molar concentration are all synonyms. 4 different ways to say the exact same thing. This question says, what is the molar concentration? And maybe it's obvious, 350. But I need the milliliters to be in liters. The quick way to do it is to go, I've got 355 milliliters, move the decimal point, 1, 2, 3. This is 0.355 liters. I can do it a little more formally, but realize the quick way to do this, if it's in milliliters, is just to move the decimal point. But the formal way to go is, cut those moles, so I'm going to go solution. I could put soft drink here. And then the last thing I want to do is put moles on top. That's going to end in liters, moles. Got this upside down. So 355 milliliters. After you do this, you're going to have 0.355. Then you have liters. So if I go 1,000 times 0.133 divided by 355. Moles per liter. You could also write that 0.375 capital M. Either one of those is correct. I think maybe if you wanted to do it just by moving a decimal with your head, you would go moles over liters. 0.133 moles over 0.355 liters. 0.133 divided by 0.355. Is it 355? Oh, no. Did punch something wrong? Three five five. 133 divided by 355. Of course, it comes out the same. Another way to do it, if you didn't do it in your head, moles over 355 liters, and then do your conversion here. So whichever way you like to do it. I always think in terms of units canceling, but maybe that's going a little too, because I mess up plenty. This is a very simple way to do it. If you can picture, if you're given it in milliliters, you just move the decimal place 3 times. And this is a little more formal. I still have it wrong. 1,000 milliliters of 1 liter. There. Now the milliliters cancel, and you end up in moles per liter. Can't do anything right today. Try to check your learning for that one, because that's more straightforward than I make it sound. One red. We have this. And that's sucrose in the soft drink. But this next example wants us to use the one we calculated in the previous example. This is so how much sucrose is in a modest sip of this drink? And they tell us how much sucrose in moles is contained in a modest sip of 10 milliliters of this drink. and we're told the volume that we obtained from that solution, about 1/10 of a milliliter. That's what we'll be asking. You have a solution that is this molarity. It's sugar in a solution. You have this volume. How many moles of sucrose are in this volume? We know that we need to end in moles. Moles of sucrose. That means I need moles on top on this side somewhere. This M is moles per liter. So I've got moles, liters, milliliters, and I'm asked for moles. Moles only shows up here in the molarity. So I'm going to write this. Oh, by the way, if you see moles per liter, like I always tell you to do, the numerical value goes with what's on top, and you put a 1 with what's on the bottom. So I would rewrite that. They mean exactly the same thing, if this is the way you want to use it now. So I'm going to take this, so that's literally what this says. It says that. And I need to take this and a volume and put them together such that I'm going to end in moles. How many moles? How many moles of sucrose? Numerical value, unit, label. So I'll bring numerical value, unit, label over here. That tells me that this unit needs to be on top somewhere over here. The only two input values I have is this. So I'm going to take this and make sure moles is on top. That is one. So I've used this. All I have left is this. The volume needs to cancel. I'm going to write this up here, 0.10 milliliters. Label. My only problem is I need the conversion factor from milliliters to liters. So I'll put milliliters here, liters here. So now milliliters cancels, liters cancel, and I end in moles, which is what I've been asked for. 1 liter is 1,000 milliliters. That will calculate to the moles of sucrose. You with me? I did that one better than I was doing empirical formula. 0.1 times 0.375 divided by 1,000. The answer my calculator says is 0.0000375. This came out to 375 again because that's 0.1 and that's 1,000. You could write it as this, moles of sucrose. You can also go 1, 2, 3, 4, 5, 10 to the -5. So either one of those is 100% correct. If I wrote that as a question on a test, one of those would be among the answers. You guys okay with that? I didn't stop it too much here. So there is a check your learning to go with that. I wish it would. I'm going to rephrase this just because I think they tried too hard. By making real examples like sugar and Coke. Distilled white vinegar is a solution of this. Okay, here's what we're told. It is acetic acid, but that doesn't matter. They even give you this. nothing to do with anything here. Here's the facts. That many liters of solution, and there, oh yeah, we are going to need this. Because they don't give us the grams per mole. So those two things are given, and then you're asked, I tend to keep questions more simple for a test and stuff that I'll put on D2L. But we need here, we've got this many liters of solution, this many grams of acetic acid. What is the molarity? What we're going to need is we're going to need to know how many moles that is. C3H3CO2. By the way, that's called a structural formula. Let's see, two of those. Yeah, that's acetic acid. We've got one carbon there and 3 carbons there. We've got 3 hydrogens there and 1 hydrogen there. There's just one of those. CH3CO2, C2. So 1 carbon there and 1 carbon there. 1 hydrogen there, 1 hydrogen there. 3 hydrogens there, 1 hydrogen there. And then you've got 2 oxygens. Just to be complete, that's acetic acid. I'd be more tempted to just give you that. This is a structural formula that kind of gives you an idea of how the molecule is constructed. But if you had this C2H4O2, you could easily find the grams per mole. Four hydrogens, 2 oxygens. 4.04, 32, 60, 10, 60. So you got So we're going to use that to turn this into moles. I'm going to say AA for acetic acid. Grams of acetic acid over moles of acetic acid. 1 mole of acetic acid is 60.06 grams of acetic acid. 25.2 divided by 60.06. 4 and 3, this needs to be 3. My calculator says this. 419, this is a 5. So the 5, there's my 3 significant figures. The 5 rounds to 9, but that means this 19 goes to 20. At least that's how I think about it. And that's, we need that. And we have liters of solution. We don't need to do anything with that. So it's moles, liters, and that'll give us moles per liter. 0.420 divided by 0.50. 0.840, capital M. It could also be 8.40 times 10 to the negative 1 mole per liter, or M. That would be a standard scientific notation that way. So in this case, we were given grams of the solute in liters of the solution. We had to turn grams into moles, and then we could calculate moles per liter. You follow me? This one, check your learning. I wrote this question. I'll make it less wordy. I would say, calculate the molarity of, you've got 6.52 grams of COCl2. You've got a C and an O. This is a lowercase o. That means that lowercase o goes with the C. So that's the symbol. It's actually cobalt. COCl2. And they're nice enough to tell us it's 128.9 grams per mole. So now we don't have to go calculate the grams per mole. They just gave it to us. Dissolved in an equal solution with total volume of that's the solute. The solution volume is millimeters. We need to turn that into liters, and we need to turn the grams into moles, and then we're just going to put the moles over the liters, and that'll give us the molarity. You with me? Everybody good? Grams cancel, we end at moles. .52 divided by 128.9. Three significant figures makes this. We've got 0.058 and change. Three significant figures is there, so 3.0506 moles of COCl2. If you just wanted to move the decimal, what is that in liters? What is it? Point.
Is it
1, 2, 3, and there's the decimal. 0.0750. You've got to keep that O, because that's three significant figures. So the rest is moles of solute in 0.0750. 0506 divided by 0.0750. Three significant figures is there. The 6 rounds of 4, so 0.675 moles per liter. I could put that as a capital M. I could go 6.75 times 10 to the 1 M for standard scientific notation. You guys okay with that? Did y'all solve problems like this when you took chemistry before? Let me ask you if they ever did this. Did you ever see it like this? 52 grams, COCl2. That puts me moles up top. Solution. I did this first, and then I used that to do the rest the way I did it. You ever see it done like this, all in one big shot, all the way across the board? You can do it that way. It'll come out exactly the same if you like to do it that way. The way I like to cancel units, I'll sometimes do it that way, just because I'm paying attention to units. And let me point this out. Did you ever do it like that? That's really common. Students come to my class have seen that. It's the train tracks method, I think they call it, but it's literally the same thing as this. You just take away those vertical lines and you're doing real math now. It just means this times this times this times this. All right, so whichever way you want to do it, you'll come up with an answer. I think it's more logical to break it into pieces when I'm explaining it to people. All right, that was the check you're learning. You got the markers down here. Of a 5.30 M solution. Thank you. No extraneous BS. Here's a question, and just answer. Okay, NaCl, it says solution, but they probably mean water, but it doesn't matter here. Okay, how many grams here? So, when you see this volume of this molarity, the best way to set it up, and that's already in liters, so we don't have to convert that, 250 liters. And I'm going to say solution, and then you put your moles per liter here. Moles per liter. Moles, now, gotta flip this over. Moles per liter, and then we're going to have grams per mole for NaCl. That's going to have 1 over grams. So I'm going to turn this over. What if I did, let's do this. I'm going to write the molarity first. It is 5.30 moles of solution. Like I said before, turn that into 5.30 moles per liter, and then turn that into 5.30 moles over 1 liter. That's what I've got here, 5.30 moles over 1 liter. This, I think, is superfluous, but it's really popular, but everybody ought to just write that. When we write density, we say grams per milliliter, and there's not a special letter you replace that with, so I don't know why molarity has a special letter. But okay, so I'll write it like that. That's M, flipped over. And now I'm going to put liters up here. Liters of solution. Over 1. Liters cancel, then we got moles. So liters cancel, we've got moles on top, moles on the bottom. 1 mole of NaCl. If you look at the periodic table, Na, there's 1 of them in that formula. What does it weigh? Cl is 35.45. This is 22.9 something. What is sodium? 91. But there's 1 of each, so I can just add it straight up. 5, 6, 7, 5, 6, 7, 8. So there's the grams per mole of NaCl. But I would write it like that, maybe with the label. This isn't part of the calculation. Anyway, 58.44 grams per mole. Liters cancels, moles cancels, and we got the grams. And that's what we're asked for. How many grams of NaCl? Grams of NaCl. Exact, all the rest of it. 3 significant figures, 3, 4 significant figures. So we want to end in 3. 5.30 times 0.250 times 58.44. Calculator says 77.433. Keep in nose, the 3 does not round to 4, so 77.4. That's how that one's done. That one is sprayed nice and clean. This makes me happy. Acetic acid. Okay. Learning. CaCl2. They're nice enough to say 110.98 grams per mole, so we don't have to calculate it ourselves. R of a 0.200 or Since we just did one, I know how we start. So we're going to put, we want moles to be on the bottom. Moles of solution and 1 liter of solution. Again, I got that from this. That's what the M means, moles per liter, which is 0.200. So that's what I've got right here. How many liters do we have? We have 200. Do you want to move the decimal, or should I put a conversion factor? 1, 2, 3, 0.2500 liters. And then we're going to use the grams per mole. In some sense, 110.98 grams per mole is shorthand for this more formal. So I want moles to cancel, so I'm putting moles on the bottom. And that'll end on ACL2. 0.200 times 0.2500 times 110.98. My calculator stopped at that. Exact. 3 significant figures, 4, 5. We're keeping 3. The 9 rounds to 4, so 5.55 grams. The concentration before was determined to be that molar solution and grams of acetic acid are in it. If it were me, I would specify molarity. I wouldn't just say concentration, because there are other ways to do concentration. Amount of solute over amount of solvent. You can do moles of solute in kilograms of solvent. There's various ways to do it. But I would call that molarity. Okay, we have that much solution, that molarity solution, that many grams. What is the volume? Easier to pick on the textbook. All right. Because you want volume, you're going to write this you're going to write this flipped over so you have liters on the top. Moles of AA are in 1 liter. I'll say SOL again. Start like that. Moles. So in that we need. Why did I say that? I want liters on top. What I said, I think. 1 liter on top. Acetic acid. Okay. Did they give us the grams per mole of acetic acid? We calculated. Anybody taking notes? What was the grams per mole of acetic acid? Was it 60? What was it? I calculated again. But
It was 60.06.
so they're referring back to that other problem. So 60.06 grams per mole. Moles cancels, we want to keep liters. Now grams, and we're given this grams of it. And that's it. Moles cancel, grams cancel, that'll give us the liters. What volume? .6 divided by 0.839 divided by 60.06. Exact. 3 significant figures, 4 and 3. So 1, 2, 3. This is what my calculator says. That's 3, so it's 1.50 liters. And it is solution, if you want to put a label on it. Moles of AA, moles of AA. Grams of AA, grams of AA. We're left in liters of solution. So that's why it's L with solution in parentheses in the quotation marks. You guys okay? We're almost to dilutions. Let me do one more of these. Check your learning for 318. What is the volume of a 1.50 molar KBr solution? That contains 66 grams of KBr. This involves moles per liter. We're asked for liters. We're given grams. We're going to need grams per mole for KBr. 1K, and there's 1 Br. What does the periodic table tell you? K is on the left. 39.10. And Br is
79.90.
it's one of each, so I can just add them straight up. 9 and 9 is 18. 7, 8, 9, 10, 11. So 118 grams per mole. So now I've got everything I need. We want to end on volume, so I'm going to write 1 liter of solution is 1.50. That's this. That's 1.50 moles per liter. So I'm just using this flipped over with the label on it. I just erased it. What was it? 118? I just erased it. What was it? What is it? 118 is right. Grams per mole, but that's 118.00 grams over 1 mole. I want moles on top, so KBR is 118 grams of KBR. And this is how many grams we have. To make grams cancel, I'll put it on top. And that'll do it. Moles cancel, grams cancel, we end in liters of solution. Probably a more proper label would be, but it's understood what the solution is. I'll just write solution. 66.0 divided by 1.50 divided by 118.00. My calculator says 0.372881355. I'm only keeping 3, right? Exact, 3, 5, 3. The 8 rounds to 2, so 0.373 liters of solution. Or 373 milliliters of solution. Or 3.73 times 10 to the negative 1 liters of solution. Subject that frequently comes up with concentration is dilutions. Those of you who took chemistry before, I bet you remember the word at least, doing dilutions. Dilution is something here. I'll put 20 dots in there. If I took just pure solvent, pure liquid here, not the dots, and I poured it in here, and got it up to here, maybe it's not obvious. There's 20 dots in here and there's 20 dots in here. So this would be some concentrated solution. And if I needed something that's less concentrated than that, I can take the pure solvent, pour it in there, and get something that's more dilute. That's a dilution. You pour the pure solvent in, and now you've got something that's a different molarity, a lower molarity than you started with, a lower concentration than you started with. You follow that? Frequently in the lab, we have a stock solution that some lab tech, and here would be one of the chemistry majors, and there'd be like like those things we have the deionized water in, there'd be one of those and it'd say like NaOH on it, and it'd tell you the concentration on it, and it'd be really concentrated. And it would just sit there, and then anybody could go get NaOH, but they're not necessarily going to need that concentration. So they have a high concentration there so you can get what you need and then pour in the pure water to get the concentration that you do need, and then you can go do whatever experiment you want with it. It's kind of the idea of having bottles of solid things sitting on the counter. You can have a solution that's ready-made to use, you just have to dilute it to the concentration that you want. So frequently we use the word stock solution when we talk about dilutions, because that's usually the most common case where dilutions come up in a lab. All right. Those of you who took chemistry before, do you remember that? M1V1 equals M2V2. This is the math you use, the formula you use to do this. Your book says C1V1 equals C2V2. And yeah, that's still true. C here stands for concentration. So any of the weird concentrations you might use, which sometimes it's moles per kilogram of solvent, or what are the other things? Molality. Anyway, we're sticking strictly with molarity. So I'm just going to do this because the M stands for molarity. So the M means the concentration, but we mean in molarity. So I'm using M. And the V is the volume that you might use. So I'm going to do M1V1 M2V2. Maybe I should use a C there because I'm going to say this is example 3.19. I guess I'll use a C because they do. And we're going to stick to the ones with molarity. All right. If is diluted my numerical values over here to a volume of 1.80 liters. For these types of problems, notice you got 4 variables, and as long as you've got 3 out of 4, you can solve all 4. Just typical algebra. And yeah, we do have, this is a C concentration, this is a V volume, this is a V volume. We're solving for one of the M's, or we're solving for the other C. As long as you can CV1, C2, V2, as long as you can identify what's what when you read the problem, then it's just plug and chug. You have this many liters of this molarity, and it's diluted and then becomes this. The 1 is sort of like, here's your starting state, and 2 is your ending state. This is saying your starting state is 8.50 liters, with 5.00 molarity. So L there, 0.850 liters, this is it. 850 liters, and your starting concentration is molarity. And then it says, by addition of water, you add copper nitrate is diluted to a volume, so the new volume is 1.80. And we're solving for that, that's X. So I just use C2 for that. And the rest is plug and chug. You with me? This is I usually take this and just solve it for what I'm looking for. So what we're going to do is C1 V1 over V2 equals C2. You don't have to make the units match here. If this was in milliliters, you could just leave it that way, because it's really a proportionality, it's not. But to be formal, I guess you would convert it. But anyway, all I'm doing here is C1 is V1 is 0.850. V2 is 1.80. And we're going to end up in molarity for the concentration. Times 0.850 divided by 1.80. Keeping I got 2.361111. We're keeping three significant figures. So it ends up being 2.36. What's always true, if you consider the ones your starting state and this the resulting thing after you've diluted it, the volume will always be higher, the V2 will always be higher than the V1, and the concentration will always be lower because you're diluting it. So we started with 5 molarity, we ended up at 2.36. Kind of a double check you can do if you just look at your calculations. In the one, this in general would be our stock solution that's sitting over in the corner somewhere. And we needed 2.36 molarities for what we were doing. Skip the 3 out to volume of 0.12. they say 0.01 liters of again, identify what is what here. May I let them know? Okay, so can you tell me which one is which? The key to this is being able to pick out what's what. What's the concentration 1 and the volume 1? What's the concentration 2 and the volume 2? If you can do that, this is easy. Made from, can be made from this. So you're going from here to there. So if you're going from those two, where do they go? You go from here to here. So it's in the phrasing. You can pick it out. You're going from 0.45 molar and you can use 11 milliliters if you just drop the units off. I know that's weird, but it ends up being proportionalities. But if it makes you uncomfortable, you can use 0.011 liters from there. And then, so you're getting to this from those. So 12 molar goes here, or 0.12. And this is what we're looking for. If you can do that, this is going to come out in milliliters because I left this as milliliters. They did it in liters, but it actually doesn't matter here. Here's why it doesn't matter. If I divide both sides by V2, I have C1, V1, over V2. And now I'll divide both sides by C1. If this is in milliliters, it all cancels anyway, and you just end up with a proportionality. And this would be in moles per liter, but the moles per liter cancels anyway. So I know that's weird, but it saves you steps, so I like to mention it. Okay. Solving for V2, so C1, V1 over C2 equals, I'm just going to go ahead and write milliliters. So C1, I'm going to leave the units off. V1, 11 milliliters. C2, 2 significant figures. Times 11 divided by 0.12. 0.45 times 11 divided by 0.12. But I'm going to round that to 41.3 milliliters. So volume 1 compared to volume 2, the volume has gone up. The concentration has gone down as a double check. You guys okay? Realize if you're bored, it's a good thing. Because that means you're understanding. usually in a class, you start by going, here's a chemical reaction, balance the chemical equation. Do y'all remember that? Let me skip that. I'm not going to say balance this chemical equation. I'm going to give it to you. And then we'll do something with it, because that balancing part just throws everybody off. Stoichiometry. I should probably tell you what section this is. Chapter 4, and I'm going to do example 4.8. But let me just say something about this first. 2 aluminums, 3 iodines, makes Al2O3. So the idea of balancing a reaction is there are 2 aluminums over here, that means there have to be 2 over here. It's I3. There are 3 iodines over here, that means there has to be 3 here. If I told you to balance it, that means I can give you these, and you have to figure it out. This one actually would be very easy to figure out. But this is saying on this side I have an aluminum and I have another aluminum. Over here I have an iodine, and another iodine. And over here I have only one, and everything adds up. 2 of these, 2 of these, 3 of these, 3 of these. But let me just start and show you why these are useful. Why a balanced equation is useful. So there it is, already balanced. I may or may not go back to balancing, but if I do, I'll keep them simple. Every equation I've shown you, in most every equation you ever see in an undergraduate chemistry class, there's a formula, an equal sign, and there's the answer. When you try to balance equations, and picture one that you hated that you tried to balance back when you took chemistry before, it's called an iteration. You just start by a guess with one of these, and then you go, okay, if there's 2 of those, that means there has to be 2 of these, and you might have to put a coefficient, and it goes, okay, now there's that many of those, and you go back, and you might run to a point where it stops working, you have to start over and start iterating again. Do you remember doing that? The thing is, we don't give you the analytical way to solve, like here's the equation, there's an equal sign, there's the answer. You iterate your way to it. There is an analytical way to solve these, but you would need matrix algebra to do it, and since nobody's going to teach you that in a chemistry class, because it's a higher level topic, they have you iterate, but it doesn't teach you anything going through the iterations. So I tend to stay away from making you balance these. So I'm going to skip that and go straight to what this is useful for. First thing to say is, this is a summary form of a set of relationships. There's the relationship of aluminum to iodine here. There's a relationship of the aluminum to the Al2O3, and there's a relationship there. There's 3 relationships being expressed there, and here they are. Two moles of Al, and yeah, go ahead and just stick moles in there, even though it doesn't show up there. 2, 1. I don't remember that's an I. There's one of the relationships, that's this one. There's another relationship that's summarized over there. To 3 moles of I. So that's this one. And then this one is one. That's really what this tells you. This is just a summary form of those 3 relationships. You with me? If you see a reaction like that and you're asked to do what I'm about to do, as a starting point, you could write all the relationships that are there off in the margin and go, okay, I'm using that. But truthfully, you typically only need one of these, or what you're asked to do. So let me give you example 4.8. You're told the reaction. Typically, when you get to this point, they don't make you keep balancing it yourself. They just give it to you. So there it is. They give it to you, and then they say, moles of I2. Is that I2? Oh. That's I2. There's a 2 there. 2AL, 2 of these. All right. 2 moles of AL, 3 of I2. And then 3 moles of I, 2, my bad. All right. That's actually what it says. So now if I did those relationships, that's what it would say. 2 of these to 2 of these, 2 of these to 3 of these, and 3 of these to 2 of these. How many moles of R2 are needed to react Well, you have your relationship. So this one talks about I2 and AL. It doesn't talk about AL2, I3. So the relationship you're going to want is between I2 and AL. So this is the relationship we want. You're told you have 0.429 moles of AL. You want moles of AL on the bottom. We're being asked for moles of I2. How many moles of I2? So that's the relationship. So yeah, there's only 3 relationships, but you might use it flipped over, but that's the relationship. And we're going to turn out to want to flip this over. We want moles of I2 on top. So I'm going to put 3 moles of I2 on top, 2 moles of AL2 on the bottom, not AL2, AL, and that'll solve it. So skipping all the BS about trying to balance it, that's why it's useful. So the answer, 0.429 times 3 divided by 2. Oh, in this case, these coefficients are exact, so that's exact, that's exact, that's exact. So this is where all of our significant figures come from. My calculator says 0.6435. 3 significant figures, right? Yes. The 5 rounds of 3. That's the answer. You guys good? We get to skip balancing. That makes you happy, right? There's one case where it's useful, but it needed, but it'll come up later. There's only one place I would bother to do. I'd rather just skip to what's useful. Do this. Speaking of, I'm using grams in this calculation. Here's the reaction stoichiometry. When I ask you these, I'm just going to give you the reaction. What is that? The reaction is free calcium OH2 plus 2H3PO4. So you're given that, and yeah, you're asked to do something with it. But just as a reminder, it's the relationships that you're going to use, or at least one of the relationships that's there you're going to use. There's this relationship, this relationship, there's this relationship. So that's 3. I've compared this one to all 3, so now I'm going to go to this one. There's this relationship, and that relationship, so there's 2 more. And now all that's left, I go to the next one, and there's this relationship, and then that's it. There ends up being 6 relationships here. So you just start at the first one, you pair it with everything, you go to the next one, you pair it with what's left, you go to the next one, you pair it with the last one. So our relationships here are 3 moles CaOH 2 to 2 moles of H3PO4 next is 3 moles of CaOH2 to make sure that's 1 mole. Yeah, that's right. 1 Ca3, Ca3. There's 2 of the relationships. There's 1 more of these with CaOH. To 6 moles of H2O. Since there's 6, so that's the first 3. Now it's 2 moles. So I've done these. I've done those. Now I'm going to do that one. 2 H3PO4. To 1 mole. This is another case where we don't write the 1. I don't know who started that. Chemists. Chemists love to drop the 1, but there's a 1 there. Ca3PO42. Now this one, 2 moles. C. 2 moles. That HPO4 to 6H2O. And 1 more, the last 2. 1 mole of Ca3, 2 to 6 moles of H2O. There's all 6 relationships. That was very tedious to write. The truth is, I'm only going to need 1 of those. I just like to write them all so you realize if you're staring at something and you've got the problem, and you don't know where to start writing those relationships. At some point you're going to stop and go, oh, okay, wait a minute, I only need 1 of these. And then you can move on into the problem and go back to find which one you have to use. But that's the expanded content of what this summary statement is giving you. It's all those relationships that you want. This is all 6 of them written in a very summary form. That's all this is. It's a list of 6 relationships. how many moles of CaOH2 are needed to react with 1.36 moles of H3PO4. Now line this up just so it's how many numerical value moles, label. So now that I've written it, you realize I really wasted a lot of time over there. There's only one of those relationships I needed. So I did that just for the pedagogical value of doing it again. But all we need is the CaOH to the H3PO4. This one. That's really the only one we ever needed. So I just spent a bunch of time writing 5 on them that I didn't need. How many numerical value unit label? So I'm going to go equals numerical value moles CaOH2. And over here, I'm going to write the 1.36 moles I need moles of H3PO4 on the bottom so it cancels, and I need moles of calcium hydroxide on the top. So I'm going to go ahead and go moles of H3PO4, moles of CaOH2. And now I'll look back over here, and it turns out I'm using this flipped over. 1 mole of Ca3. No, that's the wrong one. CaOH. Did I write it wrong? HPO4. CaOH. It's this one, I think. Not this one. Moles of CaOH on top, moles of C3PO4. Okay, so I'm going to use this, but I am going to use it flipped over. No, I'm not. I'm going to use it as it is. 3 moles of CaOH2 to 2 moles of H3PO4. There. That's how you solve it. Cool with that? .36 times 3 divided by 2 that's it. Exact 3 significant figures. That's how you solve that. You guys all right? You're bored, right? That was example. I guess that was check your line. I want to label it, just anybody watching the video. That one and check your line. Yeah. That was a check your line for that one. Check your learning. That was that one. I'm going to start bringing. So, continuing in chapter 4, I'm going to do. Both of those that I just did, the two things on the left side of the arrow were reactants, and I was relating them. But nothing really changes if you start talking about how much of this reactant to get this much product, or if I use this much reactant, how much of this product will I get? The calculation looks exactly the same. Let's do this is 4.10. So now I'm going to involve mass. And it's just the grams per mole that ends up being what you need. GCl2 plus 2 NaOH. Already balanced for you. You don't have to balance it. So there are 6 relationships here, right? I'm not going to write them all because I'm only going to need one. And I'll see which one that is when I get into it. Now, what mass is needed to produce 16 grams of MgO2. There's a typo in there. They got a bracket in there for no reason. Okay. So notice this. Mass of NaOH, as soon as you see mass, it could say grams. Mass of NaOH, that tells you you're going to need grams per mole of NaOH. You're going to need that. And also, 16 grams of this, you're going to need the grams per mole. If grams is mentioned for it, you're going to need to calculate the grams per mole. You're going to need those two things. Let's go ahead and do it. OH 1, 1, 1, 22.99. Is that right? Is that right for sodium? Is it right for sodium? It is. It's one of each. 1 N, so I'll just add it straight up. The 99 becomes a 1. 6, 7, 8, 9, 10. Yeah, that sounds right. 40 grams of NaOH is 1 mole of NaOH. All right, what's the other one? We have MgOH2. That 2, realize that means you've got Mg, an OH, and another OH. So look here to find out how many things you have. You've got 2 OHs. So I've got Mg, one of them, H, there's 2 of them, and O, there's 2 of them. Somebody look up Mg for me. 24.31. This is going to be 24.31. This is 2.02. 2 times 16 is 32. Oh, 3, 3, 8, 4, 78.33 grams per mole. I'm going to double check. 24.31 plus 2.02 plus 32. 58? Yeah, I did that wrong. Whatever. It's 58, right? Did I do that right? Is it 58? Okay, so we're going to use these two things. And there's only one more thing we need to solve this. And as you might imagine, it's this relationship, MgOH and NaOH. And like I said before, it's all in the phrasing. I mean, if it's these two things you're working with, it's going to say, how much of this is needed to react with, how much of this is needed to react with some specified amount of this. But the phrasing might be, if I have this much of this, how much of this will be produced? Or it might say, if I've produced this much of this, how much of this reacted? But that's just the phrasing. We're relating NaOH to MgOH by this equation. So that's just in the phrasing. It looks exactly the same no matter which two you're comparing. You're just getting that relationship and sticking it into the calculation. So the relationship we want is MgOH and NaOH. Yeah. NaOH. 2 moles of NaOH to 1 mole of MgOH. 2. That's the relationship we need. 1 Mg, 2 OHs, 2. Okay, that's right. Okay, and then the only other number up here, there's these two things we're going to use. There's that we're going to use. You look back at the problem. This is what you're given in grams. So write 16 grams of MgOH over 1. We're going to need grams of MgOH 2 on the bottom to make that cancel. If you look at the things we're using this, we're using that, we're using that. Where do you see grams of MgOH? You see grams of MgOH, but there's no grams of MgOH here. There's no grams of MgOH over there. That tells you this is the next thing to put. And we're going to use it flipped over because grams is on the bottom. I should be saying MgOH too. I'm just saving myself a breath. 58.33 grams. This tells us that moles of MgOH is down here. OH2. We've used this. So what's left? We have grams of NaOH, moles of NaOH, moles of NaOH, moles of MgOH. What we need is moles of MgOH. This is the only place you see it. So you're going to use this, and we'll use it the way it is. 2 over 1. NaOH. And now we use this. Now we need moles of NaOH on the bottom. The only thing left is that. Moles of NaOH on the bottom, grams of NaOH on top. That answers the problem. Realize it's tedious, but it's straightforward enough, right? I can't take the tedious out of it. All right, so what do we get? Let's say this. That's exact, that's exact, that's exact, and these are both exact. These numbers here are all exact. There's a 1 there, there's a 1 there, so those are exact. Exact, exact. 4 significant figures, 4 and 2, so we're going to end up in 2 significant figures. $16 times 2 times 40.00 divided by 58.33, and that's it. Calculator says 21.94411, etc. We're keeping 2. The 9 rounds to 1. 22 what? Grams of NaOH, grams of NaOH, moles of NaOH, moles of NaOH, moles of NaOH, moles of NaOH, grams of NaOH. Grams NaOH. That's the answer. What mass of NaOH? Grams of NaOH. Guys okay? I'm happy to stop there. We'll do a few more like this, but realize right when I started this, it was this many moles of this, so how many moles of this? And the only thing we needed was that relationship. You could say, here's some grams of this, how many moles of this would you get? And then you wouldn't have to do the grams per mole at the end. Or you might be told, you've got this many moles of this, how many grams of this would be? And then you don't need a gram per mole here. So there is a slightly shorter version of this. Molarity dilutions, an introduction to stoichiometry. See ya.